Onward to interior mutability. And by the way, there's an example in it's going to get into cell today, and there's an example that's similar to the last one in the previous video, and that explains. There was a question before about what's the point of changing there's a variable called b, and it turns out it's sort of like a lead into the cell example, which we'll look at in a second. But yeah, if you had any questions about that yesterday, as all of us did, that gets explained in the cell example today. So let's continue. Interior mutability. The borrowing rules as introduced in the previous section are simple, but they're quite limiting, especially when you have multiple threads. If you follow those rules, then it makes communication between threads limited or almost impossible, since no data that's accessible by multiple threads can be mutated. And so, of course, we have all these types in Rust, and they use interior mutability. That's the escape hatch. So when you have that, it slightly bends the borrowing rules. And what that does is, under certain conditions, you set these conditions to make it safe. And they allow mutation through a quote-unquote immutable reference. So it's immutable, but it's actually able to mutate because there are all these rules set up to make sure that it's actually safe. In reference counting, we've already seen one subtle example, and this is kind of interesting. So you have RC and arc. They're actually doing little mutations on the inside because you have like one, 2, or 3, objects kind of sharing ownership, and so they're actually mutating number on the inside, even though they never get declared as mutable. So even though there might be multiple clones all using the same reference counter. As soon as interior mutable types are involved, calling a reference immutable or immutable becomes confusing and inaccurate, since some things can be mutated through both, which is true. And so in this case, it's probably better to call them shared and exclusive, and a lot of people do that anyway for the regular references, and it's probably it's a little bit more accurate. But of course, the syntax itself is got this mute, so you call it mutable. But technically, it's a little bit nicer to call it a shared reference. So it can be copied and shared. An exclusive reference guarantees it's the only exclusive borrowing. And for most types, shared references do not allow mutation, but there are exceptions. And this book is about all those exceptions, and so that's why it's going to call it shared and exclusive. Then there's a little note here saying, by the way, interior mutability only bends the rules of shared borrowing to allow mutation when shared. However, it does not change anything about exclusive borrowing. So exclusive borrowing still means that there are no other active borrows no matter what, and the only way to get around it or to mess it up is unsafe code, which can give more than one active exclusive reference, and that always invokes undefined behavior. So good to keep that in mind. So then it goes into it starts looking at the types that do this. So let's take a look at a few types with interior mutability and how they do this. Allow mutation through shared references, so that's like so-called immutable references, without causing undefined behavior. So they all have these strict rules that make sure that they're not actually doing undefined behavior. So cell, I like cell. People don't use cell that much, but it's nice and simple. It's for some reason it's my favorite one. So a standard cell simply wraps a T, but allows mutations through a shared reference to avoid undefined behavior. What it does is it only allows you to copy the value out if T is copy, or replace it with another value as a whole. In addition, it can only be used with a single thread, so it's pretty simple. And here's the example I talked about. So it's similar to the one in the previous section, except instead of using an I32, it's using a cell. So let's type that. Switch to VS Code. There we go. Clean that. And start typing. Function F. So this looks a lot like the one before, except it's a, let's see, it's a cell, what is it? It's a reference to a cell I32, and B is also a reference to a cell I32. Whoops, why do I have that extra? There we go. So we've got A and B, and then it does the same thing as before. So let before equals A, but this time it's a get because the cell has the get method, and so you can see you get the I32. Before, in the other example, it was it's just dereferencing, and then we're going to change it. And the way you do that is you use the set method, and then you go B get +1. So you get B, and then you set it to something greater than that. So you're changing the value of B. And then let after equals A dot get. And then finally, if before not equals after, and in this case, in the book it's that, but we don't have that function. So we'll say this might happen this time. Before we wrote this will never happen. And so that means in Godbolt, it should show up. Oh, and by the way, in the last, so in the example in the video before, I thought the book was saying that when you do, let's see, B plus equals 1, I thought the B plus equals 1 was sort of like an indication that the compiler was using that as a hint, but it only uses, it already knows through the borrowing rules. So that was just like a lead-in to say in this next example with a cell, it's actually a different situation. So the two examples kind of work together that way. So let's go to Godbolt. Rust.godbolt. And then we should see lots of code. So here's the one before, and let's see. If before not equals after, that's what we did before. Yeah, so here's the example from the last video, and you can see it doesn't even take this into account. And now it should, because, all right, use standard cell. Now it should compile. And now we can see all of this, because it actually might happen. And the reason why is because of this. Unlike last time, it is now possible for the if condition to be true. Because a cell I32 has interior mutability, the compiler can no longer assume that its value won't change as long as we have a shared reference to it. So that means that both A and B might refer to the same value, and that means that mutating B might affect A as well. So you can have a cell and you can stick in these shared references, and this might change this, might change this. It may still assume, however, that no other threads are accessing the cells concurrently, so it will know that. The restrictions on a cell are not always easy to work with. Since it can't let us borrow the value it holds, we need to move a value out, leaving something in its place, modify it, then put it back to mutate the contents. So let's do that example. But I still like cell the most, even if it's a little bit awkward here. Okay, so get rid of function f, and we'll replace it with function f. So we've got a cell with an I32 again, and we would like to, hold on, no, it's a cell of a vec of I32s. There we go. So what we're going to do is let mut v2 equals v dot take. And what it says here is replaces the contents of a cell with an empty vec. And we can see that if we go into here, you can see self. What it does is it does self replace, and then it just sticks in default. And the default of an empty vec is, or the default of a vec is an empty vec. And then finally you can go, we've got this mutable vec that we took out, and we can push this into it, and then v.set v2. So let's say you have like a, maybe we can do an assertion here. So let's do test, we'll call it f works. And then what are we going to do? We're going to say let my cell equals cell new, and we're going to put a vec of 1, 2, 3 in there. And then we're going to do f my cell, and then we'll say assert eq. And then we'll say, let's see, my cell dot get, actually take, my cell dot take, and it should be vec 1, 2, 3, 1, like that. You can see, there you go, the test passed. So we could just print it out, but it's kind of fun to do an assertion like that. So yeah, you can, when you want to, it's kind of an interesting way to work with a cell. So you take something out, make it mutable, do something to it, push it back into the cell, and that's one way to work with it. So yeah, that was cell.